Welcome to Fashion Show Reaction with Facial Recognition, where we react to fashion show videos, but with a twist. We apply facial recognition technology so that we can identify the models. We're going to do something different in this video. Instead of reacting to a fashion show, we're going to explain the facial recognition technology we use, how we use it. Then we're going to apply clustering technology to the results where we make two major findings. First, we show how we could use facial recognition to profile people by ethnicity. Second, we're going to have some fun and see what models in our training data set look like each other. Are you ready? Here we go. Let's start with a brief overview of how the facial recognition technology we use works. First, we had to create a training data set filled with pictures of models. Here is a screenshot of our training data set, so you can get an idea of where everything starts. Then, using Python, we feed this data set into the face recognition library, which serves as a wrapper or easy way of accessing the facial recognition technology found on dlib, which then locates the faces in the training images, then applies its deep learning architecture called ResNet to output a 128-dimensional vector to represent each face. But wait, what is a vector, you ask? A vector is a mathematical way of notating a scalar, which is a representation of more than one value. For example, if you're flying an airplane and air traffic control tells you to fly a heading of 60 degrees at the rate of 150 knots, they have given you a vector which denotes two values, heading and speed. How this translates into facial recognition is that each of those 128 dimensions is a measurement of the directions and distances between landmark distinctions on the face. Knowing that computers only store numbers, you might wonder how these 128-dimensional vectors are stored. They look like this, which represents one single face. Then the face recognition library takes these 128 values, and using calculations such as cosine similarity, you remember cosine from trigonometry class, right? Or Euclidean distance, and creates a single embedding value for each face. It is comparing these embedding values that makes facial recognition technology work. If the values are close enough together, depending on how you have set the parameters, then you get a match. All right, let's get down to what we are going to do in this video. Both sections of the video are based on clustering the face embeddings from the training data set. A good example of clustering is if someone gave you a basket full of multiple kinds of fruit and asked you to sort them by kinds of fruit. You might end up with a pile of apples, a pile of oranges, and a pile of figs, etc. You cluster the fruit by type. Here, we're going to cluster the faces by how they look. In other words, we're going to group together models that look like each other. But before we do that more fun, second part of the video, let's do something a little scarier, so we can show how facial recognition might be used either for good, depending on your definition of good or evil. We have just over 1,000 models in the training data set, so to find doppelgangers, we would need to run a lot of clusters. But let's try only 3 clusters and see what happens. One traditional way to take a look at clusters is to graph them. So let's graph our 3 clusters we created using k-means clustering on the training data set embeddings one at a time. Here is cluster 1 with a red X over its centroid or center point. Then we graph cluster 2 and indicate its centroid. Finally, we graph cluster 3 and mark its centroid. The axes on these 3 graphs are slightly different. So let's put all 3 graphs on top of each other and see what we learn. Not much. It looks like a big mess rather than separate piles of apples, oranges, and figs. We can see the centroids are not directly on top of each other, but the data certainly seems to be on top of itself. So did we learn anything at all by creating 3 clusters of the face embeddings? At first, it seems like the answer is no. But maybe if we use our human brains and look a little deeper, we will find we have learned something after all. Let's look into the data associated with each cluster. If we break out cluster 1 by itself and look at the actual names of the people bearing the faces in cluster 1, we can see that they are almost exclusively of Eastern African or Western Asian ethnicity, or at least their names indicate this. Not 100%, but close. Then if we do the same manual review for cluster 2, we see the names of that group are almost exclusively of Eastern Asian ethnicity. We're starting to see something here. Then when we get to cluster 3, the trend continues in that almost all of the members have traditionally European names. Wow. Even though graphing the 3 clusters gave us the impression they were junk and provided no interesting information, when we look deeper at the names associated with the faces in the clusters. And to be sure, the face embeddings do not know the names of the people to whom the faces belong. We learned that the facial recognition technology combined with clustering was able to do a decent job of determining the ethnicity of the data subjects. Think about how those findings could be used. If we wanted to narrow down marketing to targets in East Africa or the Middle East and had access to pictures of the target's faces, we could limit our marketing to people who fell in Cluster 1. But if we wanted to discriminate against East Asians by, for example, rejecting them for loans, we could reject applicants that fall into Cluster 2. There's a lot of power in this data, folks, and it can be unlocked with some fairly simple math and processing. But enough doom and gloom. Let's get to the fun part of the video. We reclustered the over 1,000 faces in the training data into 300 clusters this time, in order to find groups of models that look similar according to their facial recognition embedding values. You might ask, what did the clusters that the computer spit out look like? Let's take a look at some examples. Here we start with some pretty large example clusters that quickly allow us as humans to see that even though the computer thinks these men and women look similar, we can easily tell most of the subject's part. As we move forward to some smaller examples, you might think there are some subjects that require a second look for a human to make sure they're different people. Now that you have a feel of what the computer spit out, I can explain that I looked at each of the 300 clusters and using my human skills, tainted by my being a Westerner of course, to find what I thought were doppelgangers. Are you ready? Let's dig in and see what I found. First, I will overlay the entire cluster from which the matches were found, then slide that off, and just give you the doppelgangers and an indication of how close I think they are. If you agree or disagree with any of these matches, let us know in the comments. Okay, folks, here is where it gets even more interesting. We matched some pairs of the opposite sex. Are you ready to crank it up even more? How about when 3 models look like each other? If you do not think we could get more interesting, how about triples where the sexes are mixed? You thought we were done, didn't you? No way, let's crank it up to one group of 4 I identified who look very close to each other. But then we're going to wrap it up with the grand finale. A mixed sex group of 6 models that look very similar. Hopefully you learned something about facial recognition technology and also had fun seeing what models look like each other as discovered by that technology with some human input. See you next episode.